Hello, everyone. Hello, and welcome back to CS422 Theory of Computation. We are in Chapter 2, Advanced Computability Theory, and actually towards the end, towards the most advanced topic in Chapter 2, namely the post question and its answer to Friedberg and Muchnik. So let me remind you what is post question. Emil Post observed that when comparing the various decision problems that we and he had encountered so far, such as the halting problem or the non-triviality problem or the totality problem, all the problems we and he had encountered so far are comparable with respect to this notion of reduction that we had introduced before. Actually, we had introduced two notions of reduction. The first, many-one reduction, where the argument gets translated by a function, and then the answer to the translated input must be equal to the answer of the original problem. No post-processing, only pre-processing kind of. And the second notion of reduction that we considered is oracle during while programs, where one can make queries to the second problem repeatedly, and one can process the answers to the queries and make adaptively new queries and lots of pre-processing, and actually even kind of a dialogue between the translation and the second problem to which one wants to reduce the first problem. And with respect to these notions, it turned out that so far the problems we only knew come in steps. There's one layer of problems that are mutually equivalent. Namely, for example, halting problem is equivalent to non-triviality problem. Then there's a next level, such as the totality problem or the halting problem for while programs with oracle access to the halting problem. That is the second level. And then there's also problems on the third level, such as the question whether two while programs are equivalent, and many more such problems. But the point is, the problems not encountered so far seem to come in these levels. And Post's question was, is there something in between these levels, or do these levels really comprise all the problems? And mathematically speaking, that amounts to the question whether the partial pre-order induced by this notion of reduction is a total order, whether any two problems can be compared, or whether there may be two problems that are incomparable to each other. So there are actually two questions. So let me show you and remind you of the notion of reduction using oracle for while programs. Reduction now not just for decision problems, but reduction for function problems, functions from natural numbers to natural numbers. This was our notion. And with respect to this reduction, with respect to this partial pre-order, it's a pre-order because it's not antisymmetric. If psi is reducible to phi and phi is reducible to psi, then it's not necessarily that phi is equal to psi, but only they're equivalent. And with respect to this partial order, the problems one has encountered so far seems to come in these steps. And actually, the steps have thus received names. So this simple empty set refers to the decidable, the class of decidable problems, because the empty set is a decidable, so it's a representative of this equivalence class. This class is an abbreviation for all problems equivalent to the halting problem or its complement, such as the non-triviality problem, and it's called MTZ prime because it also consists of the halting problem for Oracle programs with no terminology will become clear later. It refers to the halting problem, but the next level that includes, for example, the halting problem for while programs with Oracle access to the ordinary halting problem. And this level turned out to be equivalent to the totality problem. And as I said, there are many more levels. One can really climb up artificially or not this hierarchy by iteratively considering the halting problem. So the n plus first level is the halting problem for while programs who have Oracle access to the nth level iterated halting problem. So it's an iterating of halting problems with the termination of while programs having Oracle access to more and more powerful oracles. But this is a linear order, the total order. Any two problems here can be compared. And Emil Post asked whether something like this here is also possible, where there are two problems that are incomparable. This is cannot be solved with Oracle access to this problem, and this cannot be solved with Oracle access to this problem. Is this possible, or is this fundamentally excluded? That seems like a very natural question about the structure of this partially ordered set. And his second question was, is there actually something between these steps? And right, so let me show. These are the two questions asked by Emil Post in 1944. And the answer, so this is the terminology, halting problem for while programs, termination of while programs who have Oracle access to the halting problem when this is abbreviated in this way. And it took pretty long, actually. If you think about it, 12, 13 years during and after Second World War until an answer was found, and the answer turned out to be that indeed such problems B and C exist that are both incomparable to each other, and secondly, that are strictly between the decidable and the undecidable problems. So these are kind of the terminologies that these are low problems. So although they are undecidable, they are not powerful enough as oracles to allow for solving the halting problem. Okay, and actually, the answer to the second question implies an answer to the first, right? Because if the two are incomparable, then it follows that they must be strictly in between the two, provided that they are semi-decidable, that they are recursively enumerable, and that's exactly the Friedberg-Muchnik theorem. So, and the construction, so Friedberg and Muchnik independently construct such problems, such decision problems, artificially, to be honest. But if you think about it, also classical computability theory started with this artificial counting estimation. How many problems are there on the one hand, and how many algorithms are there? And since there are many more problems than algorithms, there must be undecidable problems. And this was only the starting point of investigation that resulted in more and more explicit and practically relevant questions, such as Rice's theorem, crucial for software verification. And same here. So Friedberg and Muchnik's theorem should be considered as starting point, and they were the starting point to a thorough investigation of this degree structure, the structure of the partially ordered degrees with respect to this notion of reduction. So here's a theorem for your convenience. the statement says that they exist, undecidable, that will follow in a minute, but semi-decidable, that is enumerable, decision problems, A and B, subsets of natural numbers, that such that the A still remains undecidable to a while program who has Oracle access to B, and B remains undecidable to a while program who has Oracle access to A. And in particular, yes, as I said, it follows that these problems are undecidable, they're even undecidable with added power of Oracle access. And furthermore, theirs must be strictly easier than the halting problem, because any problem that is as difficult as the halting problem, such as the non-triviality problem, can be decided with Oracle access to the halting problem. But if a problem cannot be decided with Oracle access to B, then B must be strictly easier than the halting problem, and vice versa. Okay, and what we're going to do today, and this is going to be pretty complicated actually and involved, but also really, I'm going to say, the top highlight of chapter 2, remember the ramp of the sophistication of difficulty is going up and it's reaching its top now at the end of chapter 2. And after that, when we start with chapter 3, it will start very easy again. So please stay focused, try to follow. And as usual, I'm more than happy to answer your questions. So, and we're going to develop the proof. So I'm not just going to throw the proof at your face, because there's little to be learned from facts, right? We want to convey understanding. So what I'm going to do is, I'm going to present several proof attempts. And for each one, we're going to see why this proof attempt failed. And then we're going to try to mend, to repair the failure. And that will take several iterations until finally we arrive at the proof of Friedberg and Muchnik. So you can see and appreciate how they, perhaps, I'm not a historian, how they arrived independently of each other at these proofs. So what is necessary and sufficient is that the complement of A is not semi-decidable with Oracle B. Remember, being undecidable means that either it's not semi-decidable or its complement is not semi-decidable. Now A and B are claimed to be semi-decidable, so it must be their complement which is not semi-decidable even with Oracle B. And that's what we're going to try to show using an advanced diagonalization structure. And similarly, we're going to try to construct B such that its complement is still not semi-decidable with Oracle access to A. So these are the two goals in our construction. And the thing is, we're going to see why we need to construct A and B in stages simultaneously. So I'm not able so far, but nobody has been able, but maybe at some point it will be able to really just write down, this is A, this is B, verify the properties. Instead, it requires advanced diagonalization techniques, proof techniques that were similar to actually to forcing, if you, some of you are logicians, forcing independence proofs in mathematical logic, such as Cohen's proof, independence of the axiom of choice, or the continuum hypothesis. All these are proof theoretic strategies. And what we see here is kind of a computable variant counterpart to that forcing. Okay. And to start slowly, remember the very first lecture, Undecidability of the halting problem, where basically we would consider the following paradoxical problem, which is called the diagonal problem. given a white program, given an algorithm, does the algorithm not terminate on its own input? Okay, and what we've constructed, we suppose that there's an algorithm solving the halting problem, and from that we constructed another algorithm that can solve this diagonal problem, and then we realized that there cannot be an algorithm solving this diagonal problem because the existence of such an algorithm would lead to a contradiction in itself. It's a contradiction similar to the liar's paradox, like if I tell you I am lying now, that's a paradox, right? Either if it's true, then it's wrong. If it's wrong, then it's true. And similarly here, the statement that there's an algorithm which terminates precisely, which semi-decides the diagonal problem immediately in a similar way leads to a paradox and thus to a contradiction, which is the first basic example of diagonalization, namely deliberately constructing a problem which on which every single algorithm makes some mistake. That's a gist. Let me say it again. So diagonalization can be seen as an approach constructing a problem, a decision problem, such that every single algorithm makes some mistake on that decision problem, and therefore no algorithm can always answer all this decision problem always. Okay, so some algorithm may answer some instances correctly, other algorithm may answer instances correctly, but no algorithm can answer all of them correctly. Namely, in the way we construct it, we take an algorithm and design the problem so that this algorithm makes a mistake, in this case makes a mistake on its own input, and therefore makes a mistake on some input, it makes a mistake. And then take the next algorithm and a thought experiment and an enumeration of all algorithms. Remember, algorithms are enumerable. And then construct modify the problem without changing the part that we've already fixed, modifying the problem that now the next algorithm makes a mistake on the same or another, in this case on its input. And so eventually, once our infinite sequence of phases incrementally constructing the problem, we've made sure we've constructed the problem in such a way that in the end, every single algorithm makes a mistake. Okay, and this is a point where I just made to make a brief stop and show you some slide that illustrates this, because in the end, what we're talking about is infinite constructions, right? Infinite construction, and these are subtle. Let me explain why they're subtle. So here's a kind of a thought experiment to courtesy of Joel Hampkins, a logician in UK, and he wanted to give a pedagogical approach to understanding diagonalization and priority diagonalization, as we're going to encounter in today's proof. And what he illustrates is a kind of infinite game with two players. One player is you. Here, this is you. This one. And the other player is an adversary, the devil in this case. And you're going to play a game which takes infinitely long. So repeatedly, going to play like when we would the diagonalization that we did and that we will develop further in stages, trying to fool. We are trying to fool every single algorithm to force to make every single algorithm to make a mistake, some mistake, and therefore no algorithm will be able to solve the problem we've constructed. And similarly, let's try to do the same. We're trying to fool the devil. So the devil is kind of offering us a game with the following rules. You have countably infinitely many coins. That's a large number, right? Okay, and so that's you, and this is your coins, the first 6, and the dots indicate that there are many more that you have. You're rich, infinitely rich. And now the devil is offering you a game to become even more rich. Namely, the game goes in rounds, and in each round, the devil takes 1 of your coins. Well, being familiar with Hilbert hotels, you shouldn't be too much concerned with losing 1 of the infinitely many coins. And even better, so now 1 coin is gone, right? You see it's gone here. And in return, the devil offers you 2 new coins. That sounds even better, right? So you actually make money for each coin the devil takes. You get 2 new coins. Okay, and this game continues, proceeds on, and the question is, at the end of all times, infinitely long game, or you can accelerate the game, right? So if the first round takes, let's say, 1 minute, then the second round, let's say, accelerated to take only half a minute, third round takes a quarter of a minute, and so on. So in this way, you can actually play infinitely many rounds in finite time. Don't worry whether this is realistic or not. It's a thought experiment. The question is, at the end of this game, at the end of infinitely many rounds, whether this takes finite or infinite time, how many coins do you have left? Okay, this is a question for you in the chat. Right, so there's a first answer. Please answer. Right, there's no wrong answer. I mean, interesting. Okay, interesting answer. Keep going. More suggestions? Yes, wonderful indeed. We've had already a great variety of answers. The first suggestion is infinitely many coins. That is basically as many as initially. The second suggestion is that you have no coins at the end. Yes, it's okay. To be fair, it's a trick question, right? Yeah, so those of you who complain what it means for the game to end, that's a fair point. Consider it kind of like as a limit. Some suggest that same number as originally also makes sense. Oh, and here's a heavy machinery from set theory, Aleph 0. Interesting. Okay, so as I said, it's a trick question. It's a trick question because it's not a well-posed question. It's not a well-specified question, but let's dig into why it is not well specified. So, I mean, intuitively, it seems that in each round, you get 1 more coin, so that at the end of all times, you should have twice as many coins as initially, right? Which is still infinite. So not really more, but also not less than initially. That's is kind of natural intuition, but the point of this thought experiment is to challenge your intuition. And actually, I'm going to convince you that the devil, and that's why it's a devil's game, at the end, you will have no coin left at all. Okay, and that's surprising. But why is that so? To look at this, to see this, look at this coin, for example. At some point, the devil will take this coin, right? The devil will return 2 coins in return. Let's say here 2 more coins. But the thing is, the devil will also at some point choose to take this coin. So the coin that the devil has given you at some point to increase your gain will also at some point be taken by the devil. And in return, the devil will give you 2 more coins. But this will happen for every single coin, both the coins that you already owned initially and the coins that the devil keeps giving you. Each one will eventually be taken away by the devil. Why is that so? That's so because I didn't tell you, and the devil didn't tell you, in which order the devil chooses to take the coins. If you get to choose which coin to give to the devil, and the devil gives you 2 coins in return, then you can win this game big. Then you can always choose one of your original coins. You have infinitely many of them after all, to give to the devil, and the devil will give you 2 more coins and will never be able to take any of the coins that the devil has given you, because you get to choose which coin to give to the devil, namely only those that you had initially. If you get to choose which coin the devil can take. However, if the devil gets to choose which coin to take, then the devil may and will reasonably choose the coins that the devil has given you at some point and will take them away. I'll give you 2 more coins in return. But at some point later, maybe much later, the devil will also take that coin, give you 2 more coins in return. But every single coin, both the coins that you had initially and every single coin that the devil has given you at some point or another, will be gone. And therefore, every single coin will eventually be gone. It may take longer or very long, but if the devil gets to choose which coins to take, then the devil can make these choices in such a priority that in the end, you will have lost every single coin. Whereas if you get to choose which coin to give to the devil, then you can make choices in such a way that in the end, you have still infinitely many coins as initially. So that is to demonstrate the subtlety of arguing about priority with infinite sequences of construction. And I've given you this example to Joel Hankins to warn you that what we're going to do in this when we demonstrate the proof of Friedberg and Muchnik will be very subtle and very deep, and Friedberg and Muchnik have become famous for their proof for good reason. So to summarize, let's be careful when arguing about infinite processes with 2 players. And that being said, let's now resume the diagonalization proof argument. And the proof idea is kind of an adaptation, a generalization of this diagonalization method, namely to construct semi-decidable, right? That we need them to be semi-decidable sets A and B, such that every single program will make a mistake on either the set A, and every single program will make a mistake on the set B. What does this mean to make a mistake? It means it does not semi-decide the set with the other oracle. And that's what you see here. To every program, there exists a counterexample matching this X, which depends on the program, to be a counterexample such that X belongs to A, if and only if this program with oracle B terminates. Now, why is this as a counterexample? Because to semi-decide, if the program P were to semi-decide the complement of A with oracle B, then it would mean that if X belongs to the a complement of A, that is, it does not belong to A, then the program must not terminate. Whereas if X does belong to the complement of A, so that it belongs to A, then the program must terminate. So this is exactly the opposite of what a program P, claiming to semi-decide the complement of A with order B, would need to do. Let me say it again. Suppose there exists a program P, which does semi-decide the complement of A with order B. Then this program, let's call it P, according to this claim, would make a mistake on input of X. And then on input X, it behaves just the opposite way it's supposed to do. It terminates whenever it says not supposed to terminate, because it's supposed to semi-decide the complement. And it does not terminate whenever it's supposed to terminate. Does it make sense? So this here is exactly the opposite of semi-deciding, right? So what you see here is actually semi-deciding A, but we want to make sure that no program semi-decides the complement of A. And to this end, we construct to every program such a count example. Here, the count example in the classical simple diagonalization argument is immediate. It's the program itself, right? That's an input where the program we've established with this paradox, with this contradiction to make an error. And the generalization is that to every program there exists some possibly different input on which this program makes a mistake with oracle B. Okay, and the same dually for the other problem. To every program Q which purportedly semi-decides the complement of B with oracle A, there exists a counterexample, a witness Y, a witness demonstrating that this program makes a mistake on input Y, namely it behaves just the opposite way. Instead of semi-deciding B, it semi-decides the complement of B, it semi-decides B. So this is our general proof strategy. Okay, good. So now let's do that, and let's try the first approach to constructing to every program P such a count example input, and to every program Q such a count example input. We construct these count examples while we construct the problems A and B in stages, as like in the game with the devil. Okay, so here's a first proof attempt as a thought experiment. So we start with X and Y, count examples being the 0. And we start with the problems that are going to become more and more involved, decision problems, subsets of natural numbers, to be the empty set. And now we're going to enumerate all oracle while programs. Remember, they are only countably. So as a thought experiment, we can enumerate them, and then we can treat every single one in some order. That's the trickier proof, proceeding in stages, construction in stages, gradually create a count example, modify the decision problem A and B such that there's a new count example X and Y to the next program P and Q, oracle while program, and then consider the next oracle while program P and Q and make sure that also they fail on some input. And here's a construction, and if what you see here looks like it's a program code, but it's actually part of the mathematical constructive proof as a thought experiment. So computer cannot decide whether program P on oracle B accepts X or not, but for a proof technique, we as mathematicians know that either it does accept or it does not, and we can construct, if it accepts X, then we add X to this set, to the set A, and otherwise we don't. So this is a kind of the inductive construction of the decision problem A. And we're going to do the same dually for B in just a minute. But first, let's continue considering A and see what happens. In the next round, we increase X. So we've kind of already used the witness X as a counterexample. Why is this a counterexample? Yeah, because that's exactly the definition. If this program on P on oracle B accepts X, and in particular terminates, then we add X. So that's exactly the equivalence here. And otherwise we keep A. So also in this case, this is equivalence. And this makes sure that whatever happens, the program P we've currently considered in our enumeration has such a counterexample witness X. And then we move on to the next program and the next counterexample witness X here, as you see here. And now we do the same dually for the program Q in our enumeration. If it accepts the current witness Y, then we add the witness to the set, thus making sure that the program Q makes a mistake, satisfies this equivalence with respect to Y. Otherwise, we keep B and thus also make sure that it satisfies this equivalence. So either way, the equivalence keeps being satisfied and we keep fooling on and on. Now, where is this not a proof? I mean, this seems so natural. It's not a proof because, as you see, the problems A and B keep changing during our construction. So this is not a kind of one-step construction. Here's A, here's B, but A and B keep inductively changing, like in the game with the devil. And there's no, well, there is a notion of in the end, right? Because every single natural number X and Y either gets added or not get added, but there's no such thing as later removing something. So in the end, there is an end kind of a limit. Namely, the set A in the end contains all the X's where program P on input B has accepted this, right? But the thing is, we also keep changing B. And when we change B, that means that the program P with oracle B could now, after having changed B, could behave differently. And when it initially had accepted X and we change B, then maybe now it does not accept X anymore. Or the other way around, maybe initially it has not accepted X and now we change the oracle B here and then it does accept X. And thus the condition, once it has been satisfied, this condition during a later stage may start to get violated because in the later stage B gets modified. And dually also the same, if we have this condition here at some stage, but then in the next round A gets changed, and with A changing, although also this oracle behavior changes. And when it does, then that means that the condition gets violated. So in the end, A and B are well defined as kind of limits, but the behavior, the condition, the witness condition may and probably will later be violated again, so that the construction in the end does not yield such witnesses. So that's not a proof. It's not a correct proof of the Friedberg, which, I mean, they became famous, their proof is much more involved, but it's already a start. It's giving us some good idea of how to approach the problem and also what we need to modify in our proof. And please, in the single focus on this witness condition, right? This is the condition, remember, that makes sure that every program P makes a mistake on some input X, and every program Q makes an error on some input Y. So we really want this condition to be true, and it is true in every single stage. of this construction, but it later gets violated, and thus at the end it may not be true. This is not a correct proof. Okay, so first attempt in advanced diagonalization. Now let's make a second attempt, and I'm going to tell you there are 3 attempts. The third one will succeed. So in the second attempt, we try to learn the lesson from our previous proof's failure and mend this. And the idea is, instead of just incrementing x, as here, we're going to increment y considerably. Why increment y considerably? Because what you see here is the largest query made by the program P with oracle B on input X. That's if we change the oracle A on or B somewhere beyond the largest query, then this won't affect the behavior of the program P on with oracle B on input X. Let me say that again. So every terminating oracle program can make only finitely many steps. These finitely many steps can involve only finite many oracle queries. And if we modify the oracle, let's call this oracle B here, the oracle B. If we modify the oracle on some natural numbers which are not queried by the program, then the program behavior remains unaffected. We say it again. Consider program B with oracle B on input X, and let's suppose it terminates. So it makes finitely many queries to this oracle B. And now let's suppose that we, as mathematicians now prove, we modify the oracle B, which is a subset of natural numbers. We add some natural numbers, we remove some natural numbers, but we only add and remove natural numbers that have not been queried by the program B on input X. The program P on input X can only query finitely many of these elements of the oracle, some giving positive answers when the natural number belongs to B, some giving negative replies when the natural number does not belong to B. And as long as we modify B only add or remove natural numbers that are not queried by this program on running on X, then the program will not even notice the difference and will still behave in the same way. In particular, it will still terminate or not terminate. So by considering the largest query that such a finite terminating computation performs, and then adding 1, we make sure that now the behavior of the program is not affected by later changes that happen in later stages of our construction. So this is how we repair this, just incrementing the kind of witness can change the behavior of the program, because the program could have already queried the witness X plus 1, and thus adding it could change the behavior of the program, but changing the witness, which is so large that it has never been queried, does not modify the behavior of the program. That's the idea here. And dually here for X, the largest query made by program Q with oracle A on input Y, add 1, and we can add or remove X as we like, because it won't affect the behavior of program Q on A, right? So what you see here we include X, but since X is so large, the behavior of the program Q with oracle A on input Y won't change. That's the point, right? Won't change because we modify the oracle A on some elements that are so large that they are have never been queried, and will therefore anywhere be queried even if we change A. And dually here B, if we add Y to the set B, then still the behavior of this program will remain unaffected because the next element, the Y that we add, is larger than any element that has been queried before. So that's our second attempt in proving constructing these witnesses, right? This is, we've boiled down the famous Friedberg Muchnik answer to Emil Post's question to find constructing problems that have these witness properties. Our first attempt failed because it changed the sets and thus changes the behavior of the programs. And what used to be a witness is now not a witness anymore. But here we take the changes in such a way that whenever something was a witness, it will stay a witness. There's a great question in the chat. Thank you very much. In the chat, the question is, what does it mean if the oracle is a set instead of a total function? Great. Yes, indeed. So in the first part of computability, we considered only decision problems and reduction to decision problems. And now in the second part, we consider also function problems, which includes decision problems. Decision problem is a function problem where the values of the function are just 0 and 1, named the characteristic function. And we consider function oracles, but here in this part of the proof, indeed, we only consider decision oracles. That is, again, characteristic function oracles that only return 0 or 1, that only return false or true, depending on whether the argument belongs to the set or not. Thank you. That's a very good question. And I hope now I've been able to clarify. Otherwise, please do keep asking, because indeed we're really at the, this is top level. This is most advanced logic in the sense that you need a lot of background, but you do need a very clear way of thinking. And here's another very good question in the chat. What does largest query mean? Okay, thank you indeed. Let me explain what I mean. So if the program P with oracle B on input X terminates, that's the case we're currently considering, right? Program P with oracle B on input X accepts. Accept means terminate, right? That's our definition of semi-deciding. Therefore, the program P with oracle B on input X has made finitely many steps before terminating. And particularly in these finitely many steps, it has made only finitely many oracle queries as a while program. It may have queried some Y prime, some Y double prime, all natural numbers that it has queried, whether they belong to the oracle B or not, right? But since it has made finitely many steps and finitely many queries, there's a largest query that the program has made before terminating. Okay, and this is what I mean here. The largest query made by the program, and we want that to be only larger than the previously largest. So this is kind of only increasing the candidate witnesses that we may or may not add in the next stage. So that's what means by largest query. And by considering the largest query means also if we add other elements Y, for example, the largest +1, then the behavior of the program on B, previous program on B, will not be affected. So we can change that safely now. We can change the set B safely and include Y without changing the behavior of the program. We have previously considered, recall that we consider the programs in some order because they're enumerable. Okay. Good. Yes, great question. And here's another question. Yes. In the first attempt, we would here increment x and here increment y. And here we increment y, no, we increase y, and here we increase x. That seems kind of like reversing the condition, but actually it doesn't really matter in which order we do it. The point is, yeah, we can also first run the two programs in thought experiment and then increase x and y, and same here. Yeah, so that's one of the things that is not essentially. Other things that keep explaining, that keep confusing you, are really essential, namely modifying the oracle B only on some input Y that does not change the behavior of the program on previous inputs. Okay. So why is this still not the end of the Friedberg Muchnik proof? Why is this not a proof? We have constructed, to be fair, decision problems A and B such that they satisfy these two witness conditions. To every program P occurs somewhere in the enumeration. Once it occurs in the enumeration and accepts X, then we add X to the decision problem and thus make sure that this X is a witness to this equivalence, is a witness to the program P make a mistake. And if we later change B, then the behavior of program P or oracle B will still remain unaffected, because if we do choose B, then we do that in part in a region of the set B where the program has never queried anyway and thus does not change the behavior. So we have this witness conditional satisfied both for the decision problems A and B, but remember, we are interested in semi-decidable problems. These problems are now really incomparable. One cannot be semi-decidable with respect to the other's oracle and vice versa. But Post asked for the problems to be semi-decidable, and these problems are just arbitrary problems. There's no telling why these problems are semi-decidable. For example, let's suppose we try to devise a while program that semi-decides A and a while program that semi-decides B by following up our construction, right? Our construction is kind of iterative. In each stage, we either add or do not add X to A. In each stage, we add or do not add Y to B. So a program that could kind of try to follow up on our construction could also tell whether X has been added to A, whether Y has been added to B, and therefore semi-decide A or semi-decide B, except that our construction here as a thought experiment involves the halting problem. This is something we can do as mathematicians in a non-constructive proof. This is a highly non-constructive proof to obtain problems A and B that are mutually incomparable. But these are not semi-decidable because the construction of this proof involves this thought experiment of solving the halting problem repeatedly. Okay, does it make sense? So these two parts is what result in the final set decision problems A and B not being semi-decidable. They exist. They are mutually incomparable, but not semi-decidable. But this was only on a second attempt, right? So what we're now going to do is we make our third and final attempt. And to this end, recall this was our approach of choosing Y so large that in the next round, it does not affect the behavior of the programs that we have already succeeded in fooling. But now we construct the sets A and B in a more subtle way. Namely, we simulate the programs only for finitely many steps and gradually increase the number of steps. So this is kind of like a sophisticated scheduling of the two programs. So previously, you look at this here. Here is in our thought experiment, we first solve this halting problem, and then we solve this halting problem, and then we proceed to the next while programs, which is good enough for mathematics, but not good enough for computable semi-decidability. So what we're going to do is we're going to kind of dovetail all the enumerations, the enumeration of the while programs, and the enumeration of this halting problem, and the enumeration of this halting problem in a sophisticated interleaved way, so that we also get to satisfy the semi-decidability. This is what you see here. So what we're going to do now, we're to maintain two finite lists of candidate witnesses. Witnesses that may be witnesses for this condition, candidate witnesses, and then we choose one and add it from the finite list of candidates actually to the set A. So here's, you see, kind of our terminology, an example, hypothetical two lists. Let's say here, the first list is candidate witnesses for A. So this is a candidate witness for program P1 to not semi-decide the complement of A. And this is a candidate witness X2 for the program P2 to not semi-decide the complement of A, and so on. And dually here, candidate witnesses for programs. Each program has one candidate witness. Maybe a program occurs repeatedly with different candidate witnesses. Maybe one candidate witness occurs repeatedly for different programs, but these are finite lists. Here, 3 element, here 2 element for the two witnesses for this property, and the dual property for B. And now we need some terminology. Yes, you see things become really sophisticated and elaborate now, but I promise you we're already approaching the end of the constructive proof. So we call candidate witness pair program with witness to be active if the simulation of the program P with oracle B on input X is still running in our thought experiment, but now we make sure that our thought experiment can also be performed computationally, such as to result in semi-decidable sets. Otherwise, we say that the candidate witness is not active or inactive. And this terminology will make sense in a minute when we now present the more elaborate and involved construction involving this dovetailed simulation. Namely, now we maintain a counter n, which refers simultaneously to the number of steps we perform the simulation, both in our thought experiment and actually computationally, and also to the number, the largest number of a program that we're currently considering. Recall that previously we considered an enumeration of all programs, and here we consider all programs up to capital N. Recall that we can encode programs as natural numbers. And then we make this sophisticated scheduling, simulating hypothetically all programs up to number capital N for up to capital N steps. And this is, of course, computationally feasible when we have an upper bound on the number of programs and the number of steps to be simulated in order to achieve semi-decidability. So first step is we add a new candidate witness to the list. The candidate witness N is now a new program, right? Previously we would enumerate all programs. Here we just add one new candidate program to the list and a candidate witness for this program to make a mistake. And then in the list for the problem A, we consider all active programs and witnesses. Remember what it means to be active. It's a finite list. Finitely many are active. And we consider them in our thought experiment and also computationally increasing in the number of the program in its binary code. And if that program with the oracle B we've constructed so far accepts the input A, candidate witness, within n steps, right? So previously we would just consider whether it accepts or not. Now we consider whether it accepts within these n steps, which is now finally computable. Then we add it. That's the same thing we did before. And otherwise we don't add it to the set A, and thus make sure that indeed the small a is indeed a witness for program P to make a mistake, as we've seen here before, because if it accepts, then there's exactly this equivalence, which makes sure that A, as it's called now here, is a witness for program P with oracle B to make a mistake, to not semi-decide the complement. And then we mark this witness pair as inactive because it has terminated within this number of steps. So active means the simulation is still running. It is not running anymore. We have reached, made n, capital N, large enough to not run anymore. So we mark it as inactive. And then we do the same dually, what we did here for all active pairs P and A for the first. We do the same for all active pairs Q and B for the dual problem. So we replace it and we increase B with the largest, that's right, this is the thing, the largest query that has been made so far, and the largest one that has been marked active, so that all the still simulations that are still running will not be affected by our changes to the oracle. And then we add that to the list. And then we do the same dually as we did here for P and A. We do so dually for Q and B. And I refrain from spelling that out. It's just the same with P replaced by Q, A replaced by B, and B replaced by A, and so on. So, and this is the final constructive proof of Friedberg Muchnik. This is kind of the refinement of what we did before, but now with this added condition of keeping track of how many programs we consider in the enumeration only finitely mainly, and how many steps of these programs we consider, as opposed to previously only finitely many. So on a logic level, this witness condition is now still maintained, but now we also in addition gain semi-decidability, because everything that is described here can now finally also be performed computationally. There's no thought experiments solving the halting problem anymore, because everything refers to a finite number of steps, n steps, and in the next round n increases. So this is the end. This is the Friedberg-Muchnik proof. To be fair, I still haven't, the proof is not complete. There's still a lot of things to establish, for example, to make sure that the list of candidate witnesses never becomes empty, the list of active ones. And but I think that suffices as a gist with our 3 levels of making it towards more and more advanced diagonalization. And the thing is here is, what I would like to emphasize is we replace candidate witnesses in our finite list. So once Q and B was a candidate witness, then now we replace it with Q and a much larger witness, right? Y, okay? And I haven't, it's true, but I haven't explained to you why this does not change the behavior of the previous programs. It does not, for the same reasons that we had previously, because Y is still to make sure it's the largest query made so far, so that any changes we make here in B on values that exceed this Y don't change the behavior. But we keep replacing it. Recall when we talked about the game with the devil, this replacing process is a very delicate thing. It really depends on in which order we do the replacement, right? Remember, the devil would replace your coins with twice as many coins. But depending on in which order the devil or you get to choose to do so, makes a huge difference whether in the end you're there with nothing or with everything. And the same applies here. This replacing procedure is a very delicate one, and I don't have time, nor is it appropriate at this level to expand on that, why this also this works. What I want to emphasize here is why this is called a finite injury priority proof. This is a newly developed proof technique by Friedberg and Muchnik in their solution to the post problem, and it's nowadays established as a standard technique because it's finite, right? We have finite lists here. It's injury because some element that once may have been in the list here gets replaced by another element. Injury means the list or the construction gets injured at some point, but realizes we have made a wrong choice, and then we correct that. But the correction has to be performed in a very careful way with a certain priority, because otherwise in the end we end up with nothing, like you would end up with nothing if the devil gets to choose the priority in which the coins are taken. So finite injury priority proof technique, and this conversely has inspired independence proof in mathematics, in set theory, in forcing. Okay, so to summarize, the proof of Friedberg and Muchnik constructs a witness for every program P, a witness Y, on which this program makes a mistake, but it keeps changing which witness that's injury. But if one keeps changing indefinitely, then there's kind of no limit, there's no final decision problem. So it must happen only finitely many often, which is crucial in the construction. Actually, it's not really constructive. Maybe it happens only when some program P, whose number encoding is less than Q, terminates. You can maybe see that here. Okay, only programs Q whose number is greater than P, that's here. And once one has arrived at such a witness, this witness remains, and the witness condition is satisfied for this program. This program will have been dealt with, although it's the witness for this program to fail may change. The program still, once it has been dealt with, will have been fooled, and thus every program eventually will have arrived at with at least one witness. Finite injury priority proof technique. And since both the sets A and B, yeah, everything in the construction can now be done computably. No reference to the general halting problem or the halting problem within n steps. Also, everything remains semi-decidable. So that's the end of Friedberg Muchnik proof as we've presented here. I've already shown you the subtlety of repeatedly changing, infinitely often making changes, where priority really becomes crucial. And now it's the end of chapter 2. So to summarize, in chapter 2, advanced computability, we talked about while programs. We talked about the universal Turing machine theorem in our Turing machine free setting of while programs. We talked about the normal form theorem. Every while program can be rephrased as a while program that uses only one single while loop. The SMN theorem is a computable version of type conversion, which is also known as currying after Haskell Curry, or rather after Schönfinkel, less unknown. We talked about the fixed point theorem, semantic fixed points of total computable functions. And based on the very sophisticated proof, we were able to show that there are Quines programs. Every program can, without loss of generality, be supposed to, in a sense, know its own source code without having access to external memory. Then we proved the Rice-Myhill-Shapiro theorem that says that every non-trivial semantic property of a program is undecidable. Remember what it means to be non-trivial and what it means to be a semantic as opposed to a syntactic property. Then we introduced Oracle while programs that can make Oracle queries, which gave rise to this hierarchy of more and more undecidable problems, where every next step is this halting problem, the question of termination of a while program that has Oracle access to the previous level. And we saw that every next level is strictly more undecidable than the previous one. And finally, we talked about post-problem, establishing that are undecidable problems that are incomparable. None of them can be solved with Oracle access to the other, and that are also semi-decidable. That was the final third iteration of our more involved proof, the proof technique invented being finite injury priority method. So that's all for today. That's all for chapter 2 on computability theory. And we'll start with chapter 3 on Thursday. Thank you very much for your attention and goodbye.